Okay, let's explore this. Welcome to the deep dive. We're all about taking these big, complex topics and, well, making them make sense, making them fascinating. Today, we're going on a bit of a cosmic journey, not just to the edge of our solar system. We're actually pushing right through its outer skin, if you like. And this isn't just some line on a chart. It's real. It's dynamic. A place where, science is happening right now. We're diving deep into the heliopause today. That's the boundary, incredibly far out, where our sun's influence, all that energy it pumps out, finally kind of fades into interstellar space. Yeah, the great beyond. So our mission here is to unpack this boundary, explore the surprising wall of fire that our robot explorers found, and really get a handle on what it means for us here inside this bubble and, our place in the galaxy. And guiding us, we're incredibly fortunate to have an expert whose work has really truly shaped how we understand space.
Welcome.
Glad to be here. It's a fantastic topic. So let's start at the basics. Maybe visualize our solar system. It's not just planets going around the sun, right? It's more like a giant bubble.
Exactly. That's the perfect way to think about it. We call it the heliosphere. It's
Yeah.
this huge region, sort of bubble-shaped, maybe even tailed, that's constantly being inflated by plasma from the sun.
The solar wind.
Precisely, the solar wind. And this bubble, this heliosphere, does something crucial. It acts as a shield. It protects us, the whole solar system, from a really significant amount of nasty cosmic radiation coming from outside.
Ionizing radiation, right?
Yeah.
I think Alexander Dessler coined the term heliosphere way back in '67.
That's the one. And what's really fascinating is how this solar wind works. Just imagine it streaming out from the sun, billions upon billions of kilometers, totally unimpeded. As it travels, it basically carves out this cavity, this bubble, within the stuff that fills the space between stars.
The interstellar medium, or ISM.
Right, the ISM. And the shape of this bubble, well, it's not a simple sphere, not at all. It's dynamic. Its shape depends on the strength of the solar wind, the pressure pushing back from the ISM, and even how the sun itself is moving through the galaxy.
So it's constantly changing.
Constantly. In fact, some very recent research, just from 2020 or so, using complex computer models.
Yeah.
It suggests the heliosphere might even be shaped, get this, like a deflated croissant.
A deflated croissant. Okay, that's not what I pictured.
No,
Yeah.
probably not. But it gives you an idea of the complex, non-spherical shape we might be dealing with.
So if it's shaped like that and always shifting, mapping it must be incredibly tricky.
Oh, it's a huge challenge. But we're getting better. Think about the edge of this bubble. It's not just one simple line. There are layers. First, as the solar wind flows outward, it hits a point called the termination shock.
Okay, termination shock. What happens there?
That's where the solar wind, which is moving at supersonic speeds, suddenly slams into the pressure from the interstellar medium, and it abruptly slows down, becomes subsonic.
Like hitting a cosmic traffic jam.
Sort of, yeah.
Mhm.
And beyond that shock, you enter this really broad, messy region called the heliosheath. In the heliosheath, the solar wind isn't just slower, it's compressed, turbulent, kind of churned up.
Okay, so termination shock, then the heliosheath. Is the heliopause the very final edge then? Is it sharp?
That's the idea. To picture the termination shock, think about water running from a tap into a sink. The water spreads out fast, right? Supersonic, like the solar wind. Then it hits a point where it suddenly bunches up, slows down. That little wall of water, that's like a hydraulic jump.
Ah, okay. I can visualize that.
That's a good analogy for the termination shock. And the heliosheath, the region after that. Voyager data showed it's definitely not smooth. It's full of these huge magnetic bubbles, maybe about an astronomical unit across. That's the Earth-Sun distance.
Magnetic bubbles. How do they form?
They seem to form through something called magnetic reconnection. As the solar wind slows and gets turbulent, the magnetic field lines embedded within it can snap and reconnect in new ways. This process releases a lot of energy. It heats things up, accelerates particles. It makes the heliosheath a really complex place.
Wow. Okay, so after all that churning, we finally get to the heliopause itself.
Exactly. The heliopause is the theoretical boundary. It's the line where the outward push of the sun's solar wind is finally stopped cold by the inward pressure of the interstellar medium. Their pressures balance out. That's the key.
So it's pressure balance point.
Precisely. And it marks the definitive edge. On one side, matter from our sun. On the other, matter from the rest of the galaxy. Our solar neighborhood officially ends right there.
Which brings us, inevitably, to the Voyager spacecraft. Legendary.
Absolutely legendary.
The little engines they could, well, actually, quite big engines. They're the only things we've ever sent that have actually crossed this boundary.
An incredible achievement of engineering and exploration.
So tell us about those crossings. When did they happen? What did they find right at that moment?
Okay, so Voyager 1 hit the heliopause first. That was on August 25th, 2012. It was incredibly far out, 121.6 astronomical units. That's what, about 18 billion kilometers from us? Just staggering.
Unbelievable distance. And Voyager 2.
Voyager 2 followed a few years later, on November 5th, 2018. It crossed a bit closer in at 119.0 AU. And what they both found right at that boundary, well, this is where it gets really interesting.
The wall of fire.
That's the term that got used, yes. Both probes measured a dramatic jump in the temperature of the particles right there. We're talking temperatures reaching 30,000, maybe even up to 50,000 Kelvin.
Which is incredibly hot, like 50,000 to 90,000 degrees Fahrenheit.
Wow.
How did the spacecraft even survive that?
Right, it sounds paradoxical, doesn't it? A wall of fire suggests something that would incinerate anything passing through. But the name is, well, sensational and a bit misleading. There aren't any flames, no actual burning.
Right, so what is it then?
It's a plasma, a gas of charged particles. And yes, those individual particles are incredibly energetic, hence the high temperature. But the crucial thing, the reason Voyager survived, is the density. It's unbelievably sparse out there.
So hot particles, but very, very few of them.
Exactly. Think about it like this. You can stick your hand in a very hot oven, maybe 450 degrees Fahrenheit, and you'll feel the heat immediately because there's lots of air molecules transferring energy to your skin. But imagine a near-perfect vacuum chamber heated to thousands of degrees. You can put your hand inside, and while the few particles hitting you are very hot, there are so few of them that they can't transfer enough heat energy to actually burn you.
Ah, okay, that makes sense. There just aren't enough particles hitting the spacecraft per second to heat it up significantly.
Precisely. The heat capacity of the plasma is incredibly low because the density is minuscule. Too few particles per cubic centimeter.
So what's causing this heating? What's the physics behind it?
It comes down to the collision, essentially. The fast solar wind particles smashing into the slower, denser interstellar medium. This creates a shock wave, but not like a sound booming air. It's a collisionless shock in plasma. Pressure builds up, magnetic fields get squeezed together, and sometimes you get that magnetic reconnection we talked about earlier.
And that releases energy.
A lot of energy. It converts energy stored in the magnetic fields into thermal energy, making particles hotter, and also accelerates some particles to very high speeds.
And the instruments on Voyager could measure all this.
They could, especially the plasma wave instruments, the PWS, really clever bits of kit.
How do they work so far from home?
They have these V-shaped antennas, like old TV rabbit ears, basically. They measure the electric fields of waves traveling through the plasma. Plasma oscillates at a frequency that depends directly on its density. So by measuring that frequency...
They can calculate the density of the plasma.
Exactly. Using a formula relating frequency to electron density, it's like having a remote density probe billions of kilometers away. Pretty amazing.
Absolutely. Now, you mentioned earlier the heliosphere isn't static, it changes shape. Does the heliopause itself move?
Oh, definitely. It's not a fixed shell. It breathes, in a way. It moves in and out depending on the sun's activity cycle. When the sun is really active during solar maximum, the solar wind pressure increases and the heliopause expands outward.
Pushes further into interstellar space.
Right. And during solar minimum, when the sun is quieter, the solar wind pressure drops, and the interstellar medium pushes back, causing the heliopause to contract, moving closer to the sun.
Like a lung expanding and contracting.
That's a great analogy. It highlights how dynamic the whole heliosphere is. Its size, its shape, they're constantly in flux. We're still figuring out the exact details, of course, the data is limited, but Voyager's long-term measurements are key.
And speaking of surprises from Voyager, there was something about the magnetic field, wasn't there? Something unexpected when Voyager 1 crossed.
Yes, that was a big one. Voyager 1 found that the magnetic field just outside the heliopause in the interstellar medium was aligned almost perfectly parallel to the magnetic field inside the heliosphere.
Parallel. Why was that surprising? What did scientists expect?
Well, many models predicted something more complex. Maybe the sun's magnetic field would kind of drape over the heliopause or twist or perhaps be completely disconnected from the interstellar field. Finding them aligned was odd. At first, with just Voyager 1's data, some thought it might be a coincidence, a temporary alignment just where Voyager 1 happened to cross.
But then Voyager 2 confirmed it.
Exactly. Years later, at a different location, Voyager 2 found the same parallel alignment. That pretty much shattered the coincidence theory.
So what does that alignment mean?
It suggests a much stronger, more direct connection between the sun's magnetic field and the magnetic field of the local interstellar medium than we previously thought. It implies our solar system's magnetic environment isn't isolated, it's sort of plugged into the galactic magnetic field in a more fundamental way. We're still revising models to fully understand how this interaction works.
That's mind-bending. Our sun's influence connecting directly to the galaxy's magnetic structure. But let's bring it back home. Why does this distant boundary, the heliopause, matter for us here on Earth?
It matters hugely because of its protective role. It's our primary shield against galactic cosmic rays.
High-energy particles from deep space, right?
Yeah.
Supernovas and things.
Exactly. These particles are constantly bombarding our solar system. The heliosphere, and particularly the heliopause region, deflects a huge chunk of them. Estimates are around 70%.
70%, that's significant.
Very significant. Without that shielding, the radiation levels reaching the inner solar system would be much higher. That would have implications for satellites, for astronauts on long missions, maybe even for Earth's atmosphere and climate over geological timescales.
But is it a perfect shield?
Not entirely perfect. Voyager 2 actually detected some interesting variations. It found regions, almost like porous holes in the boundary, where the levels of galactic cosmic rays suddenly spiked.
Leaks in the shield.
Kind of, yeah. It shows the boundary isn't uniform. There are complexities we're still uncovering. But overall, it's a vital shield.
Okay, so the Voyagers are now beyond the heliopause in the interstellar medium proper. What are they telling us about that region?
They're giving us our first direct measurements, which is incredible. Those PWS instruments we mentioned are key here, too. Voyager 1, for instance, measured the electron density just inside the heliopause at about 0.055 particles per cubic centimeter. Then, as it moved further out, say to 146 AU, the density increased to about 0.12 particles per cubic centimeter.
So it got denser further out?
Yes, suggesting there's this sort of boundary layer just outside the heliopause within the very local interstellar medium, the Via Voyager 2 saw something similar. Its first interstellar density measurement was around 0.039 particles per cubic centimeter.
So both probes saw this jump in density, like 20 to 50 times denser outside than inside.
That's the magnitude, yes. It's a striking confirmation that there's this compressed region just beyond our bubble, which actually aligns with some much older indirect measurements made using radio astronomy techniques decades ago.
Amazing how it fits together. What about other things thought to be out there, like the hydrogen wall or a bow shock? Did Voyager find those?
Good questions. The hydrogen wall is a region where neutral hydrogen atoms from interstellar space pile up as they interact with the edge of the heliosphere. They get heated and compressed. And yes, evidence for it was detected, first by the Voyagers back in the 90s, and later confirmed by the New Horizons spacecraft, the Pluto probe, in 2018. So the hydrogen wall seems to be real.
Okay, one down. What about the bow shock, like the wave in front of a boat?
Right. The idea was that if the sun is moving fast enough through the interstellar medium, it should create a shock wave ahead of it, like a boat's bow wave. We see these around other stars like the red giant Mira. They definitely exist.
But do we have one?
It seems. Probably not. Data from another mission, IB-EEX, the Interstellar Boundary Explorer, which launched in 2008, suggests our sun's speed relative to the local interstellar cloud isn't quite high enough to form a sharp bow shock.
So more like a gentle wave than a sharp shock.
Exactly. More of a bow wave, perhaps. The interstellar medium kind of flows around us more smoothly than we initially thought.
You mentioned IBX. That mission didn't travel out there, did it? How did it study the boundary?
No, IBX stayed in Earth orbit, but it used a really clever technique. It detected energetic neutral atoms, or ENAs.
Energetic neutral atoms.
Yeah. So when fast-moving charged particles from the solar wind interact with slow-moving neutral atoms from interstellar space out near the boundary, they can exchange electrons. The originally fast particle becomes neutral but keeps its speed, and the originally slow particle becomes charged. These fast neutral atoms aren't affected by magnetic fields, so they travel in straight lines back towards the inner solar system.
And IBX could detect them.
Exactly. By mapping where these ENAs came from, IBX created the first global maps of the interaction zone at the edge of the heliosphere.
And what did those maps show? Any surprises?
A huge surprise. IBX discovered this totally unexpected feature, a bright, narrow ribbon arcing across the sky, emitting far more ENAs than anywhere else.
A ribbon? What does that mean?
We're still debating the exact cause, but it told us the interaction isn't smooth and uniform. The interstellar magnetic field outside seems to be playing a much bigger role in structuring the heliosphere's boundary than we'd assumed. The IBX data, along with data from the Cassini mission at Saturn, also strongly supported the idea that the heliosphere is more bubble-shaped than comet-shaped, which was an older idea.
So much we're still learning. Looking ahead then, what's next? How do we keep exploring this frontier?
Well, the Voyagers are still going, sending back data, though their power is dwindling. But we have new missions coming. There's the Interstellar Mapping and Acceleration Probe, IMAP. It's set to launch around 2025.
Will it go out there too?
No, like IBEX, IMAP will observe from closer to home, near Earth, but it will use much more advanced instruments to detect those ENAs and also sample particles coming directly from interstellar space. It should give us a much higher resolution dynamic map of the heliosphere's boundary and how it interacts with the solar wind over time.
So mapping the weather at the edge of the solar system.
In a sense, yes. And beyond that, scientists are actively studying concepts for a dedicated interstellar probe.
A mission designed from the ground up to go truly interstellar.
Exactly. The idea is to send a probe maybe 10 times faster than Voyager, aiming to reach perhaps 1,000 astronomical units out.
1,000 AU, that's incredibly far.
It is.
Yeah.
But it would give us an unprecedented view, not just crossing the boundary, but really exploring the nature of the interstellar medium far beyond the sun's direct influence. It would be a multi-generational mission, but the science return would be phenomenal.
It really puts the Voyager achievements in perspective, doesn't it? As we wrap up thinking back on everything we've discussed, it's just amazing. From that wall of fire, which isn't really fire, but this incredible energy exchange to the heliosphere breathing with the sun's cycle, and that surprising magnetic connection to the galaxy.
It really changes how you view our little neighborhood in space.
Absolutely. And understanding this boundary, it's not just abstract science. It's fundamental to future exploration, to protecting our technology and ourselves, and just grasping our real place in the cosmos.
And maybe a final thought. Even though the Voyagers have crossed the heliopause, they haven't exactly found smooth sailing. They're still detecting changes, gradients in plasma density, shifts in cosmic ray intensity, even further out.
So interstellar space isn't empty and uniform either.
Apparently not. It seems the space between the stars has its own structures, its own boundaries and waves. The Voyagers have left our bubble, but they're now entering the complex ocean of the galaxy itself, getting the full picture of our local galactic neighborhood. That's likely going to take decades, maybe centuries, and many more missions. We've only just begun.
An incredible journey still ahead. And that really highlights why, for you listening, you should keep asking these questions, keep exploring. Because as we found today, the edge of our solar system isn't an ending. It's a dynamic, fascinating beginning to understanding the vast universe beyond. Thanks so much for guiding us through that today.
My pleasure. It's always exciting to talk about.
Until next time on The Deep Dive, keep looking up.